Okay, today the goal are Maxwell's relations. These things are cool. And they are specifically cool because thermodynamics is useful because some things are easier to measure than others. This is what we've been building to, is the relationship between all of the thermodynamic potentials. Let me rephrase this for a second. So the thermodynamic potentials, we have the Gibbs, we have internal energy. Actually, I'll do it this way. We have internal energy, we have Helmholtz energy, we have enthalpy, we have the Gibbs energy, and we have entropy. And I'm going to write this as TS because really you want all these units to be the same. So there's a connection between all of these, and that's within the Maxwell's relations. Okay, so starting with G is equal to H minus TS, we know that H is U plus PV minus TS. And then just like I did before, for infinitesimal processes, we can look at all of this in terms of dG, and that equals du plus pdv plus vdp minus tds minus sdt. Okay, so now du is equal to dq minus pdv, and I'm going to specifically consider only pressure volume work. I'm assuming that we're not having non-pressure volume work for this example. Okay, so then we plug that in here, and this becomes dq. And I should also say that dq is going to be reversible, equals tds. All right, so my dg is then equal to tds minus pdv plus vdp minus tds minus sdt. And I think I forgot a minus pdv in here. Okay, so if that's the case, yeah, so this should be plus. Right, so now I've got, there we go. So this is du, and then this pdv comes from here. So this cancels, and this one cancels, and I'm left with dg is equal to vdp minus sdt. This is different than the very last video that you watched, but the process is the same. So when I tell you, you can't just go in and say, well, which equation do I use? It depends. This is the fundamental thermodynamic equation. dg is equal to vdp minus sdt. I know everyone loves dg is equal to dh minus minus tds. But this assumes constant temperature conditions. This assumes constant pressure conditions. This is not constant pressure, and this is not constant temperature. So it depends on how you define your process. Okay, so this is the fundamental equation. And what do I want to say about it? Aha! Go team. So I'm going to erase and then start with the fundamental equation. Make sure you can follow all this mathematics, by the way, and that you see how I did this. Okay, so that we know that the Gibbs function is a function of pressure and temperature, which means that I can take the total differential, and that's how the Gibbs changes when I change pressure, holding temperature constant, dP, plus how I change the Gibbs when I change temperature, holding pressure constant, dt. See any connection? So because I know dg is equal to vdp minus sdt, and I also know that dg is equal to these two partial derivatives multiplied by their subsequent differentials here, that tells me that this is equal to volume and this is equal to minus entropy. Amazing. So what's great about that, and actually let me rewrite it, so partial g partial p at constant t is equal to volume, and then I've got partial g partial t at constant pressure is equal to negative entropy. So why do you care? Just like you learned so much when we were looking at enthalpy versus temperature, and you had a curve that looked like that, and you could tell me, well, Allison, well, first of all, this would be kind of cool. You know it will never go down. It'll never be a negative slope on this one because you know that dH dt, or should I say partial h partial t at constant p, is what we define as the heat capacity. So the slope of that enthalpy curve as it changes with temperature contains information about the system of the heat capacity. Likewise, if I want to look at Gibbs as a function of temperature, I'm going to have a decrease, and that decrease, that slope, is going to be related to the entropy. And I know it's going to go down because I have a negative sign here. And also, like Gibbs versus pressure, same thing. The slope of that line is going to give me my volume. So back to that quote that I told you, thermodynamics, is useful because some things are more easy to measure in the lab than others. If there is a quantity that you need, say entropy. Entropy is very difficult to measure sometimes. You can actually just go in and see how the Gibbs changes as a function of temperature. Ta-da, you have your entropy. That's pretty cool. So there are analogies to just like this. You can do this with any of the thermodynamic potentials, internal energy, enthalpy, Gibbs, we just did, Helmholtz. And when you do that, you get some really cool relationships. Here's an example of one. So one of the relationships is the partial of the Helmholtz with respect to volume at constant temperature is your pressure, or is related to your pressure with a negative sign. And then the same thing, you've got partial A, partial T, Helmholtz with respect to temperature, constant volume gives you your entropy. You have all of these different relationships depending on which system that you're looking at in terms of the thermodynamic potentials. So cool. Okay, so now I'm going to talk about Maxwell's relations. So the goal for the derivation is going to be to get to one of Maxwell's relations. I'm just going to give it to you up front. So partial V partial T at constant P is equal to negative partial S partial P at constant T. That's so cool. Oh my gosh. And you might look at this equation and say, I really don't care, Allison. Big to do. They're just some partial derivatives. Until you're in the lab and you need one of them and you don't have it, but you can measure the other. So let's talk about how you can get to this. And this is using Euler's reciprocity theorem. So I have partial G, partial P at constant T is equal to the volume. And likewise, I have partial G, partial T at constant P is equal to minus S. I keep checking my notes because I want to make sure I don't make any mistakes. There's a lot of moving parts here. Okay, so based on Euler's reciprocity theorem, what I can do is I can take this whole thing and I can say partial T, and then that'll give me d partial T of dg dp at constant T, and all of this at constant P. Oh, I should say that this is going to be a constant P. And likewise, I can do partial P at constant T. So this gives me partial P dg dt at constant P at constant T. And that is equal to minus partial S partial P at constant T. Likewise, this one is equal to partial V partial T at constant P. And I'm going to put a little colon right, or semicolon right here, so you can kind of see that there's a, I'll just do that. So I've got two different ones going on. Okay. So now Euler's relation is right here. And this is saying that if I have partial x of partial f partial y at constant x at constant y, that's equal to partial y partial f partial x at constant y at constant x. Look at these differences. Partial x, f with respect to y. Partial y, f with respect to x. They've switched. xy, yx. tp, pt. Go team. Okay, so that tells you that these two things from Euler's relation are equal to one another. glorious, which means that this and this are equal to one another, which you knew because I kind of gave it to you. But check this out. Partial V partial T at constant P is equal to minus partial S partial P at constant T. This is not just true for this one particular system. There are, oh, I don't have the page. There are a lot of Maxwell's relations. One in particular, let's say we've got partial T partial P at constant S is equal to partial V partial S at constant P. That's cool. So there's a lot of these different relationships. And I can't emphasize how important they are, except that they are. But also, it's not that you have this relation and you call it a day. It's that you have empirical data for how the volume itself is going to change as a function of temperature. So we know that if we have some sort of system, let's say we have a liquid, and the volume changes as a function of temperature as some A, V, actually I was going to say it's some A value plus V, well, BV plus CV squared. Let's say it follows some sort of polynomial and you've got these coefficients for this particular type of material. And you want to know something about the entropy of the system. Well, how on earth are you going to measure anything about the entropy of the system? In fact, I challenge you. When have you measured the entropy of any of your experiments before? We've talked about it. You've talked about it all the time. Oh, entropy's increasing. I guarantee you it is. But how? How is entropy increasing? Well, if you know what the empirical relationship is of this system specific, so now they've got chemical character within this empirical model of how the volume changes with temperature, you set that sucker equal to constant pressure, or keep constant pressure, take the derivative of this with respect to temperature. Ta-da! Oh, sorry, these shouldn't be V's, these should be T's. Oh my gosh. It's been a day. It's like 5 o'clock in the evening. I'm ready for coffee or a beer. Okay, so now you can take the temperature derivative of this here and you'll get a function. Guess what? That function is now equal to partial S partial P. And if you keep temperature constant at that point, well, you've already taken the derivative. Then you've got, let's see, this is B times T. Actually, it would just be B plus 2C times T is now equal to minus ds dP. Well, take this, B plus 2C times T, multiply that by a dP is equal to minus ds, integrate both sides. Now you know the function of your entropy with respect to pressure. And I come up with this off just on the fly because I cannot tell you what the equation will be. This is the beauty and the challenge of this material, is because it depends. We don't know how this material will be. It might be that this is temperature independent. It's a solid. It doesn't change with volume, which means it looks like this, which means the dV dt is going to be 0 because you don't have any change in volume with respect to change in temperature. If, however, that's true, that means the ds dP is 0. Well, is the pressure going to change the entropy of the system if it's a block of lead? No. And so you can learn a lot about your systems by not having to go in and take the data if you know the relationships to some of the other thermodynamic potentials. That was a mouthful. Okay, pause and rewatch this one a bunch of times. I hope it's helpful. Come to me with questions. Okay, that's Maxwell's relations. And there's a bunch of them. Anyway, go look them up. There's a whole bunch.